let's hope that the others will be here shortly. So last week we ended, remind you, last week we ended with almost the last theorem in the section 2.7, but we didn't get to cover the last proposition, the last theorem. And this was needed for the assignment question on the previous assignment. So that's why I sent an announcement over the weekend that if you're confused about an assignment question, this might be needed to solve it quickly. And if I also offered office hours on Monday, but in case you missed that. So to finish this, let me just go over this proposition in the first few minutes of the lecture, and then we have to move on to week 8. We are in week 8 right now, and we'll be talking about the determinant. Because our lecture section is a little bit behind, we'll need to speed up a little bit and catch up to the other sections. But in the future, we'll make sure that there's no assignment question that can't be answered with the material that we've covered so far. Any questions before we start with the lecture? All right, so let's wrap up section 2.7. Let me just remind you that the section was about changing the basis of a vector space. So if you have two different bases, then there's a matrix that sends the coordinate vectors in the first basis to the new basis coordinate vectors. And we found in this proposition that we covered last time at the end that this matrix, which we call the change of basis matrix for obvious reasons, is precisely the matrix for the transformation, which is the identity transformation. So if you consider its matrix in the bases alpha and beta, this will be exactly the change of basis matrix from alpha to beta. There's a discussion that that you can look at if you want. One of them is that these have to be invertible. This is very interesting because what is the inverse for going from so the notation was I alpha to beta. Well, if you go from alpha to beta and then you go back from beta to alpha, then it should better not change anything, because if you go from one to the other, to the new basis, and then you go backwards, this is supposed to be the identity transformation, the identity matrix. So this means that the inverse of the this notation is not ideal. I wanted to, this is actually the ID transformation. So this means the change of basis matrix I alpha beta is the change of basis matrix going backwards, just by the property of matrix multiplication. Matrix inverse is a matrix that multiplies with a matrix to the identity matrix. All right, so the last proposition that we couldn't cover last time is looks at what happens after transformations when we change the basis of the domain and the codomain. Well, it turns out that if you have a transformation and you consider the basis alpha and beta for the domain and the codomain, and you compute its matrix as we've had before, and then you change your mind, you want to change the bases to alpha prime and beta prime on V and W respectively. Well, then the matrix of the transformation in the old bases, alpha and beta, is sandwiched with both change of basis matrices. So this is the change of basis matrix on V, so on the domain, and this is the change of basis matrix on W. So if you sandwich the original transformation, this is the original matrix, then you get the new matrix representing the same transformation, only in a different choice of bases. So you just multiply the matrix from the left to the right. So Benjamin asked something in the chat. If you what you can do is, so there's a special case if you have a transformation from going from V to V. But in this case, it's supposed to be prime is lower and on the right, because you. So let me maybe address this question with the diagrams. So you have T. Oh, thank you. Yes, that's what I mean. Yes. So this one would have to be alpha prime as well. That's correct. So you could switch alpha and alpha prime by just taking the inverse, and this is also done in the book. So if you look at the book, then you can how to look at this special case with the domain and the codomain are the same, and then it really is the case that T from alpha to alpha prime, sorry, in the new basis alpha prime is equal to T alpha. So we change the basis from alpha to alpha prime. Then we would have the transformation, the identity map in the basis alpha prime to alpha, and we would here go from alpha to alpha prime. But it would be nice to have the same matrix left and right. So therefore, what we can just do is we can take again the alpha prime index to be on the lower index, and then we just take the inverse of this. So this is in the book if you want to know more about this. And then this next definition is very natural after this proposition. Well, what really happens here? So we have a matrix and we sandwich it with two invertible matrices. So we multiply it with a matrix and its inverse on the other side. And this is really, if you forget about transformations, this makes sense just for matrices. So we consider two matrices, A and B. In this case, it would model abstractly just what happens for transformation. So this would be A, this would be the base matrix B, and then we can sandwich it with P and P inverse on the left and right hand side. So whenever there are two matrices A and B such that they're equal, when one of them is, this is called conjugated, so we multiply to the left with P, the right with P inverse, then we call them similar. And the idea is that, so the intuition is that if A and B are similar, then they represent the same transformation going from V to V. And here we assume that they're square matrices in different bases, alpha and beta. So you can think of similar matrices as just being different representations or different representatives of the same transformation, only for different choices of bases. Any questions? Yes, Claire, you have your hand raised.
I just want to clarify that from the T above, from alpha to beta, these two transformation is similar, right?
So can you repeat this question? It's a bit quiet.
The transformation from alpha to beta and from alpha prime to beta prime, they're the similar, right?
So you mean these change of basis transformations?
The one on beside it, the two beside it.
This one?
Yeah.
Yes. So if I understand this correctly, what you asked is that this matrix will be similar to this matrix because these change of basis, well, in the case that W is V, so they have to be the same vector space. But in that case, these matrices will be similar. And the similarity, the property of being similar is transported or is carried by these two matrices. So this will be the P in the definition below, where B, the one matrix, has to be multiplied with P and P inverse in order to be equal to A.
Oh, okay. Yeah. Okay. Thank you.
So there was a question by Yuan. I could. Yes. So to prove this, I don't want to go into this because I have to go to the next section very quickly. So to prove this, you could just create any basis alpha, and then you can get a transformation B from B. So you have T sub B, and then you have to find a new basis. So find a new basis beta in exactly the way such that P will be the change of basis, the change of basis matrix. So it's the other way around. Usually we have two bases and then we find the matrix going from one to the other. In this case, because you want P to be exactly the change of basis so that the new transformation matrix will be the A. So this has to be P. We have to design the new basis alpha, the new basis beta in exactly a way that P will go from alpha to beta. The book explains this in a paragraph below this definition. This one. All right, so we could have done an example, but if there are no more questions, then let's go to next week's content. So what I want to do today is to go through determinants. And we'll start just with the 2x2 matrices, but eventually we'll talk about n-by-n matrices tomorrow. So to motivate this, because a determinant is just an abstract function, you might wonder why do we need this? And to explain why we would need this, let me pose the question: when is a 2x2 matrix, which is just its form, invertible? And to answer this question, well, I've given you an algorithm that places A, B, C, D together with the matrix 1, 0, 0, 1 inside this double matrix, or whatever you want to call it. And then there's an algorithm so that when we row reduce this, we'll get the inverse of A on the right-hand side. So first of all, to do this, so I want to do this algorithm. I want to apply this here and then see what can we see, what should be assumed for this algorithm to work. Okay, so first of all, from previous proposition, we know that the rank A should be 2. Therefore, we can assume that either A or C are non-zero. If A and C were non-zero, you could see that the whole left column is zeros. And for that reason, it could not have rank 2. So either A or C is 0. And because it doesn't really matter which one, if A was 0, then I could just switch the columns and I would have a non-zero entry on the upper left. So this means without loss of generality, this is the shorthand form. we can assume that A is non-zero. So this means now what I would like to do is I would like to reduce this. So let me, so the first step is I subtract the C times the first row from the second one. So I'll have a 0 here. I have a D. No, sorry, I want to let me multiply this second row. There's many ways you can do this, but there's some of these are quicker than the others, and some of them are nicer. So I'm allowed to do this because A is non-zero. If A was 0, you can multiply in the row reduction with a 0 coefficient. And now I can subtract C times the first row from the second row, so that I'll get 0 here. I'll get AD minus B times C, and the first one is unchanged. I also have minus C, A1 and 0. Okay, so this looks pretty good already. So in just 2 steps, we've created a 0 here without any ugly any ugly fractions. And now if you continue, now it's about it's helpful to divide the first row by A and the second row by whatever this thing is. So this so that we have already ones on the diagonal. So let me do this in one step. So we have 1 B over A, 1 over A, and 0. And the other entries are 0 and 1. And notice that in order to divide by something, we've already said that A is on 0, so that's fine. But AD minus BC has to be non-zero in order to divide by it. So we just in good faith just say, well, let's assume this is non-zero. And then we get here a number C divided by AD minus BC, and here we have A over AD minus BC. Okay, we're almost done. One last step is to kind of get rid of this entry, this B over A here. So this isn't exactly a nice inverse on the right-hand side, but it'll simplify in a bit. So now we just subtract B over A times the second row from the first one. So the left-hand side will be this, and the right half will be less nice, but it's we can just compute it. So this is going to be 1 over A plus B over A times we take this into account C over AD minus BC. So I just have a minus because I said subtracted the second row. I have nothing changes here. AD minus BC. I have A over AD minus BC, and I have B over A. Sorry, minus. I subtract B over A times the second row. So I have AD minus BC. Okay, and then this right-hand side will be, oops. This whole 2x2 matrix will be the inverse. Now we can clean this up a little bit, and we can simplify. In which case we get this is 1 over AD minus BC, and then you can do some simplification of these terms, but what you will get is dA minus C and minus B. So if you divide first of all by 80 minus BC overall, and then you just combine these two fractions, then you get this result. So what does this observation tell us? Well, if we assume that this term is non-zero, we're able to compute the inverse with this algorithm that I showed you. And second of all, we see that if it was non-zero, then this inverse wouldn't exist, because then we'd have something zero in the denominator. This isn't exactly a waterproof proof of this, but you could say that if and only if this term is zero, it makes sense to invert this. So what is this expression that we need to be non-zero, and why does this exactly, and how does this behave? So the natural definition is, let's give this a name, because this is very useful for analyzing 2x2 matrices. So I define the determinant as a function going from 2x2 matrices into a real number, and I just define it to be this expression that we found above, AD minus BC. So this definition, just by the observation above, we can see that it is the 2x2 matrix is invertible if and only if this expression, the determinant of A, is non-zero. Then our algorithm works. And in particular, if the determinant of A is non-zero, this means that either A or C have to be non-zero. This is so that our initial assumption is also satisfied. This follows from this, so that we only have to assume that this is non-zero. And then it's just to for further discussions, let me give you a different way of thinking about this. So we can think of a matrix always as its columns. So when you consider this matrix A, B, C, D, then you can just think about these as vectors, the column vectors. We've done that multiple times before. So this is X and this is Y. Okay, and then you could think of the determinant as a function. So the determinant is a function of the columns. At this point, I guess it's good to make also another remark. So that some books and some sources we could also work with rows. So rows and columns are interchangeable here. We could have just taken AB as a vector and CD as a vector, but I think for notational purposes, it's clearer if you use columns, the columns of a matrix as vectors. So everything that I'm going to say about columns in this lecture and tomorrow is exactly the same as for rows. And if you read the book is using rows. It's exactly the same. The same arguments holds. Just replace the words columns for rows, literally. Okay, so this proposition in the book, and this is already material from 223, so I'm not going to go too deep into this. But if you have two vectors in R2, then they span a parallelogram. So let me just draw R2. Then any two vectors, X and Y, which make up columns of a determinant of a matrix, for example, they span a parallelogram. Of X and Y. So the determinant, and that's the proposition, the determinant of X and Y, of the columns, or as the matrix containing the columns A, X and Y, is equal to the area of this parallelogram. And just by drawing parallelograms, you can see that no matter how you draw them, it always makes sense to kind of have some parallelogram. This is just another example. And if you draw them parallel, these arrows, then you can see that the area is equal to 0. So if the determinant is equal to the area, which this proposition, which that has a proof in the book, which is very geometric. So I'm just going to skip this in the lecture, but you can go and read this if you like. If the area is 0, if and only if the x and y are parallel, because then the parallelogram is just a line. There's no volume in this parallelogram, no area. But two vectors in R2 are parallel if and only if x and y are linearly dependent. So this means that the determinant is 0 if and only if the columns of the determinant of the matrix are linearly dependent. Any questions about this first page? Any about this introduction, this motivation? Okay, so let's make one more observation. Why this determinant is how we can view this intuitively. So as before, a matrix determines a transformation, and if you just pick the basis, the standard basis, so the basis alpha, which is 1, 0, and 0, 1 in R2, then this matrix A, B, C, D will give us a transformation from R2 to R2. So we usually call this T sub A. And so if you multiply the matrix, this is something that I just wrote here, but let's just verify this. So T sub A of the first basis vector is equal to A, B, C, D times 1, 0. And if you multiply this, you can see that we recover a vector which is exactly the first column. So this is exactly the first column of the matrix. So this is the this is X, the first column, where A was written as in terms of columns as X and Y. And likewise, if we apply T to the second basis vector, then what we get is the second column, B and D. Okay, and now the observation that I want to make here is that there's a few things that just string together nicely. There's just many loose ends, and we can, with this observation, attach them. So when is the transformation T sub A invertible? And that's the same as being isomorphism. It happens if and only if it is injective or surjective from R2 to R2. Remember that one of them is enough if V is equal to W. So if you have the same domain and codomain, then either surjective or injective implies the other one, and therefore bijectivity. But now the determinant of this matrix, is non-zero from the previous observation that we made from the proposition on the last page, if and only if the vectors, the columns X and Y are linearly independent. So now if you draw this again, let this just from this idea before that this is a transformation that sends 1, 0 to AC and 0, 1 to BD. Just think of this as 0, 1 and this as 1, 0. And now we just write so this is the transformation T sub A, and we see that this sends the first vector to X. So this is T of 0, 1, and this is T of 1, 0. So this should be Y. And this is T of 1, 0. So this should be X. And now when is this not injective? In which case would this transformation sending this vector to this vector and this vector to this vector not injective or not surjective? Any idea? So it happens exactly. Yes, exactly. Yeah, precisely. So Jagat and Sam were in the chat that when X is equal to Y, so let me write that down. So if and only if, well, X doesn't have to be equal to Y, but you could say that X is a multiple or is parallel, is linearly, i.e. X is parallel to Y. I mean, this notation, I hope no one gets confused about this, but it means X is parallel to Y. The image of T sub A is just a line and not or two. So if X and Y span the image of this transformation and they are on the same line, then the image is just a line. So it's not surjective. So if we have now had kind of three statements, and in total, we can see that this very much agrees with like these statements. They're all perfectly aligned that TA is an isomorphism. So it is injective and surjective if and only if the determinant is non-zero. So this means that the determinant of A non-zero is equivalent with X and Y linearly independent. This is equivalent with TA being an isomorphism. I.e. invertible. So the reason that this is nice is because instead of trying to find the inverse or trying to show whether it's surjective, all we need to do, according to this observation, is to compute the matrix of the transformation, unless we already have it. Then compute the determinant, and then we know everything about the transformation, if it's invertible, if it's surjective, all these things. Any questions? So I'm going at a faster pace today because we need to catch up to the other sections. This doesn't mean that you should be scared to ask questions, so please still interrupt me and ask for details at any point where there's something unclear. I'm just trying to catch up with the other sections so that we will be the same content as the others. All right, so so there's a discussion where we could draw these. Let me save this for later, or if you want, you can think about this after the lecture, and we can maybe talk about this in the office hours if you're interested. But I guess the idea is hopefully clear now that one of them that these transformations defined by them, the parallelograms, might be of zero area or positive area, depending on what the determinant of this is. So I would like to make a remark about this determinant and its kind of properties, because so far I've just guessed that there's some kind of expression depending on a 2x2 matrix, and it has it indicates properties of the matrix. And eventually we want to move on to higher dimensional matrices, or larger size matrices, n by n in general. And we need some kind of intuition. We need some kind of abstract basis, some mathematical tools in order to define, in order to be able to educated guess what the n cross n case is. So first of all, this determinant, let me just remind you, the determinant of A, B, C, D is AD minus BC, and you can just think about this as taking the diagonal, you multiply the elements of the diagonal, and then you take the off diagonal, the other side, and you just subtract the product of these. So you can see that this is linear in both arguments, and what this really means is, if you have the determinant, you think of this as functions, as a function on vectors. Linear is nothing new. We've talked about linear transformations. The only difference is a linear transformation has one argument. Here we have two arguments, and I'm claiming that the determinant of x plus z, comma y is the same as the determinant of x plus y plus the determinant of z, comma y. So same procedure as before. When we have the determinant and we have a sum or scalar multiplication, so let me do x times c times x, comma y, then this is the determinant, this is c times the determinant of x and y. And of course, I said here in both arguments, so that's very important. It's not just true for the first argument, but I want to just say this is the same for y. So we could also have y plus u and then expand this as a sum. And this is something you could really, you can check this for the given definition of the determinant, so that if you actually take, if you actually compute the determinant, of a plus u, b, c plus v, d, then this means that the first column is now a sum. It's being unfortunate. So this is now a sum of two different vectors. So this is exactly the same case that we have here. And then you just compute this with the definition above, and you can verify that this is indeed linear in this in the first argument. Okay, so let's move on with the properties. There's more that the determinant can do. It's alternating. So what does alternating mean? So if we think about the determinant as a function of x and y again, then if we interchange the columns x and y, then we get minus the determinant of y and x. And again, so you can check this. This one's actually quite quick. So we know that the determinant of x and y, or of, we say a, b, c, d, is equal to ad minus bc. And when we introduce a minus sign, so we have minus bc minus minus ad, then we see that this is exactly the determinant of the matrix bd ac. So that indeed we switched around these two columns. And finally, the last property just means normalized. Well, the determinant of the identity matrix, which is just this matrix with ones in the diagonal, is equal to 1. So this should be 1. These are all properties which are true, because if you just compute this times this, then just these two ones and then minus nothing, you'll get 1. So this is clearly satisfied. So we found that these 3 properties hold for our this guess that we've made in the first page, and this is not a coincidence. So the book actually the book has a different approach to determinants, and it takes quite long until they get to the definition and all these properties. But it's a very elegant definition that the book chooses. The book calls this the area function on the two vectors for a parallelogram. And so then among all the functions that we could consider on 2 vectors in R2, I mean, there's this many functions that you could write down. Just saying that f of x of y might be something dependent on x and y. But among all these, we can select those that have these 3 properties above. So we could say that these properties above, remember that was multilinear. i.e. in this case, linear in both arguments. It was alternating. And it was the fact that f of 1, 0 and 0, 1 should be equal to 1. Then the claim, the proposition here is that there's only one such function. So it's like having a wish list of for defining a function, and it turns out there's just one function that satisfies all these properties. So the determinant is naturally defined as this one function. It's a bit more abstract, but it's going to be very helpful for the future when we define the other the n by n matrix determinants. Okay, so let's have a discussion, because there's a lot of theory, a lot of abstract math. So let's try to think about this discussion. Can you show that this property that we've shown above, that if 2 vectors are actually linearly dependent, can you show that the determinant has to be 0? And can you only use the properties above? So this means, can you only use these 3 properties, that it's linear in both arguments, it's alternating, and that on the identity matrix it's 1? I'll give you 3 or 4 minutes. If you have questions, then just write in the chat, or ask right now, immediately. Maybe as a hint, the last comment by Jensi is very, very helpful. So this x and y are linearly dependent is exactly equivalent with saying that x is equal to c times y for some c, for some real number c. So if they're parallel, if they're multiples of each other, then they're linearly dependent. And the question is, what is the determinant of x and y? Let me zoom out so that you can see the properties. Any suggestions? Anything you came up with? So when the hint says that that x and y are multiples of each other. Oh, okay. So Benjamin wrote something in terms of a scalar multiple of y is part of the definition. Okay, so that's a very good idea. Let me just start with this. So Benjamin said that we just replace x as the multiple of y. So we just say that this is equal to determinant of c times y with y, and now we need to use some. So this is just by assumption. X is equal to c times y. Yes. So now we need to get rid of c because it's linear in both arguments. We can write the c in front, and then we just have the determinant of y, comma y. And then as the last step, what we use is alternating. So now if you change these two y's, so if you put the second y in the first slot and so on, then the rule above is that we pick up a minus. So this is the rule. It doesn't matter if x and y are equal in this case. But let me write this down. So this is minus c determinant of y, comma y. But the expression hasn't changed. So you can see that if two things are equal, so this means that this expression has to be equal to a minus expression. I don't know if this is clear if I write this. So basically, if you have this expression and you have the same expression with a minus sign, then there are two numbers which are equal. Number one is equal to minus itself, but this is only possible if the expression, which I just highlighted in green here, has to be equal to 0. So this is the general technique. If you have a number a real number, and you know that a is equal to minus a, then 5 is not equal to minus 5. Minus 3 is not equal to minus 3, which is 3. Only 0 is equal to minus 0 because it's 0. So this is just what I mean by an expression can only be minus itself if it's 0. Right, and then in that case, we see, so this implies the determinant of x and y are indeed 0 because we assume that they're linearly dependent. And this perfectly agrees with what we had at the beginning, because this is equivalent, just as a further explanation. So x is c times y means that the parallelogram looks like this. So the parallelogram has 0 area. Well, if c is 0, then it means that one of the vectors is 0. So if Yardan asked what happens if c is 0. Well, if c is 0, then this vector x is 0, and then you have a family of two vectors where one is 0, and then it has to be linearly dependent. So in that case, I guess you could also maybe Yardan is actually asking this question. So and this could be also a good question that I could just bounce back to the class in the last minute. what is the determinant of 0, 0, BD? So this means if one of the vectors is actually 0, the first column vector, then well, we can just compute that this is 0 times D minus 0 times B, and this is just 0. So as long as if any of the columns, I mean any, I'm already thinking about the n by n case, but if either of these two columns is 0, then the whole determinant is 0. Oh, so in here, this C is not an element of the determinant. This is just a scalar. I hope this is not confusing you. So I wanted to, in the beginning, remember in the beginning, I was talking about what happens if, so if the entries, if A and C are non-zero, then the rank is, and also B and D can be both 0, then the rank can be expected to be 2. And in this case, this is I guess this is a really good observation here. In this case, the rank is either 1 or 0, but not 2. All right, so tomorrow we'll continue with the determinant of n by n matrices. And just to give you something to think about before we end, the goal will be to construct a determinant for the n by n matrices. And the best way to start is to require the determinant to have very similar properties to what the 2x2 determinant has. So this means that we want a function that is multilinear, alternating, and normalized. And then we are in a very lucky case where there's a proposition that says on 3x3 matrices and also later by n by n matrices, there's just one function that satisfies all three properties. So we can just find a formula for this, and then we can practice computing n by n matrix determinants. All right, that's it for today. We left this discussion blank, but if you have questions about this, then please go over this. This is a good way to practice what we've talked about today. And if you stay around for the office hours, some office hours are right now from 4 to 5. Then I'm happy to talk about these discussions or any other questions. So let me first stop the recording. So that's the official end of the lecture.